This video is for section 18.3 about reversible reactions and equilibrium. The learning goals are to understand what happens at the molecular level in a chemical system at equilibrium, and to know three stresses that can cause a change to the equilibrium position of a chemical system. So there was some vocabulary words in those learning goals. We'll make sure we discuss those. The first learning goal is to understand what happens at the molecular level in a chemical system at equilibrium. In almost every chemical equation we've seen this year, the arrow has pointed to the right only, indicating that the reactants convert into products. In reality, many reactions can occur in reverse. So instead of using a single arrow that points to the right, it would be more accurate to use a double arrow, one pointing to the right, one pointing to the left. The double arrow indicates a reversible reaction. This is a chemical reaction in which the conversion of reactants to products and the conversion of the products back to the reactants occurs at the same time. Here's an example reversible reaction. 2SO2 plus O2 produces 2SO3. But notice the double arrow indicating that the two SO3 molecules can decompose, creating the two things on the left side. In the forward direction, this is a combination reaction. In the reverse direction, a decomposition reaction. Let's consider that example reaction occurring in a closed container. At the beginning of the reaction, there would be a lot of the reactants, SO2 and O2. And there wouldn't be any of the product SO3, not at the beginning of the reaction. So the forward reaction occurs at a quick rate. Remember, if you have a high concentration of reactants, then the rate of the reaction is faster. However, as those reactants are used up, the forward reaction will slow down. Less concentration of reactants, slower reaction. At the same time, the amount of the product SO3 has been increasing. So the reverse reaction will start to happen. At some point in time, the rate of the forward combination reaction will be equal to the rate of the reverse reaction. That's equilibrium. Chemical equilibrium is a state of balance between the rate of a forward reaction and the rate of a reverse reaction. At chemical equilibrium, both the forward and reverse reactions continue, but because their rates are equal, there is no net change in the amounts of the reactants or products. Another point to realize about chemical equilibrium is it is a dynamic state, not a static state. What that means is that that point of equilibrium can change. When a reversible reaction is in equilibrium, the equilibrium position refers to the relative concentrations of the reactants and products. That is, what are the concentrations of the reactants, what are the concentrations of the products at the point in time when the reaction is in equilibrium. Here's an example. A reaction converts A to B. So we're just speaking in general A to B instead of naming actual chemical compounds. It's in equilibrium when the mixture contains 10% A and 90% B. Write a chemical equation that shows this equilibrium position. Like any chemical equation, you write the reactant first, then the arrow, and then the product. We're going to use a double arrow to show that this is a reversible reaction. But when we draw the double arrow, we're not going to make them the same length. The forward reaction will be a much longer arrow than the reverse reaction. And the reason is, when the reaction is in equilibrium, there's only 10% of substance A and 90% of substance B, meaning there's 9 times more of this product substance than there is of the reactant substance. So this reversible reaction favors the forward reaction. Here's example 2. A reaction converts C to D. It's in equilibrium when the mixture contains 85% C and 15% D. Write an equation showing this equilibrium position. So we have C, and then an arrow, and then the D. The arrows are not going to be the same length. The forward arrow will be shorter than the reverse arrow, because at equilibrium, 85% of the substances in the reaction are C, and only 15% of the substances are the D. This reversible reaction favors the reverse reaction. After discussing the concepts of reversible reactions and equilibrium positions, let's take a look at this next learning goal. Know 3 stresses that can cause a change to the equilibrium position of a chemical equation. Here are the 3 stresses. First, changing the concentrations of the reactants or products will cause the equilibrium position to change. Second, changing the temperature of the system will cause the equilibrium position to change. And third, changing the pressure will cause the equilibrium position to change. There is a principle in science named after a scientist whose last name was Le Chatelier. Le Chatelier's principle states, if a stress is applied to a system that's in dynamic equilibrium, the system changes in a way that relieves the stress. The system will change to overcome the stress. Let's look at an example of that. Here is a reversible equation. H2CO3 produces CO2 plus H2O, while at the same time, these 2 substances combine together to create the one on the left side. The arrows are not necessarily equal in length, but with my computer, I don't have any way to type a double arrow symbol where one arrow is longer than the other. So please understand that the arrows are typed the same length, but in reality, one arrow is probably longer than the other, indicating that either the forward reaction is favored or the reverse reaction occurs faster. Number 1, explain what happens to the equilibrium position if CO2 is added to the system. And remember Le Chatelier's principle. When a stress is applied to the system will change in a way that relieves the stress. So if you add CO2, if you increase the amount of this substance, how will the equilibrium change? How will the equilibrium position change? It will move to the left. It will favor the reactants. The reason is this principle in purple ink. If there is more carbon dioxide, how can you overcome that change? By using up that carbon dioxide, by having the carbon dioxide react with the water to make more of this substance on the left. Number 2, explain what happens to the equilibrium position if carbon dioxide is removed from the system. The equilibrium position will shift to the right. The reaction will favor the products. Another way to think of that is the forward reaction will increase its rate. Here is the reason. If the CO2 is removed, meaning if there's less of this product, how will the system respond to overcome that? It'll try to produce more of the product to replace that CO2. So the forward reaction will speed up. Number 3, explain what happens to the equilibrium position if H2CO3 is added to the system. What will happen if you add more of this substance? How can the chemical system compensate? If you add more of this, then the equilibrium position will shift to the right to favor the products. because that's how you can overcome the change of adding more of this substance, by using it up, creating more of the products on the right side. Here is another example. N2 plus 3H2 produces 2NH3 plus heat. And the reverse reaction is the 2NH3 plus heat can produce the N2 plus 3H2. Again, I'm only able to type arrows of equal length, but in reality, one arrow could be longer than the other. Number 4, explain what happens to the equilibrium position if heat is added. So if you add more of this, what will happen to the equilibrium position, meaning which arrow will be longer? The left arrow will be longer. The reaction will favor the reactants. The reverse reaction will increase to use up that extra heat, and that will produce more of the substances on the left side. Number 5, explain what happens to the equilibrium position if heat is removed. How will the system compensate for that? Well, it needs to replace that lost heat, so the forward reaction needs to speed up. The forward arrow will be the longer of the two arrows, and a way to write that in words is you can say it favors the products. If a chemical reaction involves reactants and products that are gases, then changes in pressure can affect the equilibrium position. N2 gas plus 3H2 gas produces 2NH3 gas, and notice it's also reversible. Number 6, if the volume of the container enclosing the reaction is decreased, then the pressure will increase. Explain what happens to the equilibrium when pressure increases. Think about this in terms of Le Chatelier's principle. How can you overcome this stress of the particles in the container having increased pressure? You could decrease the amount of particles in the container. If there's less particles, then there will be less collisions with the container and less pressure. So how can you decrease the number of particles? On the left side of the equation, there is 1 molecule of N2 and 3 molecules of H2. There are 4 molecules on the reactants side of the equation. On the right side of the equation, there are 2 ammonia molecules. Which side has fewer molecules? That's the product side. So to overcome the increased pressure, the forward reaction can speed up, changing 4 molecules into 2 molecules. Less particles will bounce around in the container, and there'll be less pressure. So the equilibrium position will shift to the right. The reaction will favor the products. Number 7, if the volume of the container enclosing the reaction is increased, then pressure will decrease. Explain what will happen to the equilibrium position when pressure decreases. Well, how can the system overcome that change of pressure decreasing? It can overcome the change if it increases the number of particles bouncing around in the container. It can increase the number of particles if the reverse reaction occurs at a faster rate, because the reverse reaction is changing 2 molecules into 4 molecules. So the arrow that points to the left would be a longer arrow than the one that points to the right. And in words, you can say this favors the reactants. Observe that in the case of pressure changes, the way that the stressor is relieved is by increasing or decreasing the amount of particles in the system. And you use the coefficients in the equation to see the relative number of molecules on each side. Here are some check for understanding questions. I'll pause the video for you to work on these, and then we'll take a look at the answers. Here's the answer for number 1. And here are the solutions for number 2. This concludes the video about reversible reactions and equilibrium position, and how the equilibrium position can change when certain factors change. Remember that equilibrium position simply means the concentration of each substance involved in the reaction. So how do those concentrations change when something about the situation changes?